Good day. We are going to discuss our design plate for Machine Design 2 called Design of a 30-ton capacity 1/2 straddle crane. Is presented by Gutierrez John Victor Carlo, Racho Ernstwell John, Shanna Ray Julian, and Dylan Jefferson. That's right. For the introduction, a straddle crane is a machine that is known for its high versatility as it can be used in many different applications as they can transport the required cargo either vertically or horizontally in a manner. Straddle cranes are used to stack or load containers to different trail bed trucks. A straddle crane is similar to a normal crane wherein it uses ropes in order to lift or lower a payload. It is composed of several components such as a frame, the lifting assembly, winding motor, telescopic spreader, suspension, tire and brake assembly. And to control all of this, there is a cabin where an operator will oversee and control the vehicle. This is a sample picture of a straddle crane machine lifting a 40, what I believe is a 40 feet ISO standard container. So what are intermodal shipping containers? Straddle cranes are mainly used to transport and stack shipping containers, which is officially called intermodal shipping container. An intermodal shipping container is a large standardized container that is used for intermodal freight transport. An intermodal freight means the container can be transported through a variety of means such as road, railway, and ships. In this project, the student will design a straddle crane that will accommodate the dimensions and load weight for an ISO standard container 20 feet with a standard height. The student will specifically focus on the given dimensions and the capacity provided by the ISO 668-2013 Series 1 freight containers, classifications, dimension, and ratings. A revision of this classification has been published in ISO 668-2020, but because of the life of shipping containers and the early release of the ISO standard freight container revision, many freight containers use the 2013 standard and not have yet adopted the 2020 revision. So this is a table of the standard dimensions of the ISO 20 feet standard height container from ISO 668 2013. We can see the common maximum gross weight is 30,480 kilograms, and ISO maximum gross weight is 36,000 kilograms. So when lifting a shipping container, several configurations can be used depending on the machinery being utilized to load and unload the container. ISO 3874-1997 provides information on the handling and securing of freight containers, which provide operators information on what proper procedure to use when handling a shipping container. The students are going to use two types of drives to design the lifting mechanism of the straddle crane. These are the wire rope drive for the lifting of the load and the gear reduction drive as it serves as the lifting mechanism for the horse drive of the hoist drum to the spreader. This is our 3D model of the rendered view of the straddle crane. And this is our exploded view, which contains the important parts for our straddle crane, which are first the hoist drum, then the intermediate sheaves, then the sheaves at the bottom, the wire rope, and the spreader, which will lift the 20 feet ISO standard container. Lastly, there is our gearbox. First, the gearbox itself, the gears, bearings, and this will include also the shaft and the motor, but we didn't include this here. So uh, next is Gutierrez for design requirements.
Good day, my name is John Victor Carlo Gutierrez, and I will be discussing the design requirements and the wire rope configurations. Here you can see the lifting capacity of our straddle crane, which is 30,000 kilograms or 30 metric tons. We have a lifting height of 9.2 meters and a hoisting speed of 0.3 meters per second for a full load or a 0.43 meters per second for an empty load. The required time to reach the hoisting speed was in 10 seconds, and the weight of a spreader for a 20 feet heavy-duty spreader was 3,085 kilograms. Next, please. So here is the machine layout for our machine. As you can see, we have the motors, we have the gearbox, the wire, drum hoist, the sheath, and the spreader, according in its specific arrangement. Next, please. Um, we will use a 6 by 37 type of rope as it's usually used for crane and lifting purposes. We have for the computation, we have a steel rope diameter of 48 millimeter, a wire diameter of 2.16 millimeter, and a drum diameter of 1,296 millimeter. We have a bending stress of 140 Newton per square meter, and equivalent bending load of 122,640 newtons. Next slide, please. Here is the design of our sheet. Our drum rope, our wire drum in the middle, and this is the layout for our wire rope pulley system. Next slide, please. Here is our wire rope sample computation. We will use a 6 by 37 type, as it stated earlier. And we have a factor of safety of 6, as is usually used for cranes. So we will have a factor of safety of 15. For the design load, we will multiply the factor of safety to the load times the gravitational acceleration. So we will have 15 times 33,085 kilograms, which is the combination of our capacity and the load and the weight of our spreader, giving us a total load for 4,868,458 newtons. Dividing it by 4 ropes, we will get a 1,217,150 newtons per rope. Knowing this load per rope, we will get the diameter of the load, or the minimum diameter of the load needed to handle this load. We will get a diameter of the rope for 48 millimeters. Computing for the added load due to acceleration, we will get a load of 1,002.4 newtons. We will have an impact load due to starting at 655,571 newtons, giving us an effective load of 450,425.92 newtons, and an effective load during starting at 778,211.84 newtons. Effective load during acceleration is at 451,428.32 newtons. Next slide, please. These shafting calculations will be discussed by Jefferson Talan.
I'm Jefferson Talan.
Thank you.
I'm here to further discuss the topic on the shafting calculation for the intermediate sheaves. For the type of material used, we chose the AISI 4140 steel, which is oil quenched and tempered at 205 degrees Celsius. We chose this because it has a high ultimate strength at 1,795 MPa and a yield strength at 1,515 MPa. For the sheave diameter, we have a 1,296 mm and an effective load of 194,552.96 Newton. For the distance, the computed value is 69.8 millimeter. Doing a calculation on the shear design stress, we would have a yield strength at 454.5 MPa, which has a factor of safety of 3, and the shear design stress based on ultimate strength is 323.1 MPa. Based on the ultimate strength, the computed stress for the maximum load is 53.85 megapascal. To compute the diameter of the shaft, we will be basing it on the bending stress. The computed diameter is 5.39 inches and The preferred size is 5.5 inches. Next, please. For the shafting calculation on the war drum pulley, we use a similar material previously discussed, and the force computed is 389,000 newtons. To calculate the torque on the drum, we just multiply the force times the drum diameter, and the value is 504,281 Newton millimeter. Computation on the bending moment, we got a 48,638,214 newtons, which is understandable because of the heavy load we are carrying. Based on the ultimate strength of the material, we would have the computed value of 53.85 MPa. So getting the diameter again, we would be basing it on the maximum shear stress theory, and we would have a value of 14.30 inches, and we convert that to a preferred size of 14 and 3/8 inch. Next. For the bearing calculation on the war drum pulley, we chose a life of 25,000 because the machine that is created is for the cranes for bulk goods, and it is usually for the engineering industry. First is we calculate the velocity of the lifting mechanism, which is around 4.42 RPM, and our K is 3.33. Our radial load is 389,000 Newton, and we use a light shock of 1.5. The single row deep groove ball bearing is used, and we solve for the rating life, and we got a life of 3.3 million revolutions. Next, we solve for the static equivalent load, and we got a 233,000 newtons. Computing for the basic dynamic load rating, we have a 557.66 kilonewtons. Based on this number, we got a bearing that has a code of NU24CE that has a inner diameter of 200 millimeter and outer diameter of 360 millimeter, which is 58 millimeters wide. Next. For the bearing calculations for the sheaves, again, we use the life of 25,000 and compute for the operational speed again. Solving for the rating life again, we got 3.3 million revolution, and the static equivalent load for the bearing, which we got at 116,000 newtons. Again, we compute for the basic dynamic load rating, and we got this time at 278.83 kilonewtons. We searched and got a code for the bearing at NU420, which fits the specifications we needed for the basic dynamic load rating, which has an inner diameter of 100 millimeter and an outer diameter of 200 millimeter, which is 58 millimeter wide. Next.
So, I'm Jan Racho, and these are the computations for the gear requirements. So we have the load to be 778,211.8 newtons. So following the formula, the torque is equal to the weight times the radius of 0.648 meters. So we will get a value of 504,281.27 Newton meters. So also here we have the output RPM to be 4.42 revolutions per minute, and the power output equal to 233,412.29 watts or 233.41 kilowatts. Here the overall gear ratio is also 384 from the formula N in, or the RPM in over the RPM out. And here we have a table for the overall gear ratio, and the ratio for the first stage, second stage, third stage, and fourth stages, along with the angular speed in RPM and torque measured in Newton meters. Next slide, please. So here also we have the table for the helical gear train. We have the input angular speed to be 1,700 RPM, the output torque to be 504,281.27 Newton meters, output angular speed as 4.42 RPM, an output power of 233,412 watts, and an overall gear ratio rounded off to 384. So next slide, please. So in this slide, here are the summary of the torques, angular speed, velocity ratio, helix angle, pressure angle, and teeth for the four stages in our gear drive. So as we can see here, they almost have the same number of helix angle and pressure angle, but they differ in the velocity ratio and number of teeth. Next slide, please. So the shafting. So these are the different shafting for our gear drives. We have five number of shafts. Next slide, please. Nice. These are the stages. So we have four stages: stage 1, 2, 3, and 4. Next slide, please. And here are the specifications for the steel that we will be using in our helical gear drive, which are referenced from the AGMA, or the American Gear Manufacturers Association. So we have the addendum as zero point 0.8 meters, a addendum of 1 meter, the total depth to be 1.8 meters, a clearance of 0.2 meters, and a thickness of 1.57 meters. Next, please. So for the gear drive, we will take the stage 1 for our sample computation. So for the gear drive, we will follow the formula given. So the allowable stress will be divided to 3, and we will get 367.72 megapascals. Next, we will solve for the velocity factor, which is 6 over 6 plus v. And for stage 1, we will have 6 over 6 plus 845 40 pi millimeters per second multiplied by m. After this, we will solve for the equivalent number of teeth, and then we can further solve for the Lewis factor, which is shown below. So for this stage, the computed value for the teeth is 38, and the Lewis factor to be y minus 0.841 over TE. And substituting the values, we can get a factor of 0.1529. And after this, we can determine the phase width, in which here it is given at 20 millimeters maximum phase width. And then we can compute for the Lewis equation for tangential load using the empirical formula. So here we have the WT is equal to the allowable stress times the velocity factor times the pressure angle times pi times m and the Lewis factor. Next slide, please. Next, we will then compute for the pressure angle, which is cosine 25 equal to the tangent of pressure angle n over tangent 20. And then we will compute for the radial load, which is equivalent to 33.53 newtons. And the ratio factor, as shown below using the formula, Q is equal to 2VR over VR plus 1. Here, the obtained ratio factor is 1.778. Next, we will compute for the surface endurance limit, SE, to be used for the load stress factor here below. So the formula for the load stress factor is K is equal to surface endurance limit times sine phi n over 1.4 times 1 over EP plus 1 over EG. So we have obtained a load stress factor for stage 1 as 1.58. We will then compute for the pitch diameter as m times the number of teeth, which is 1 by 28 equal to 28 millimeter. And finally, for the wear tooth load, to be WN equals the pitch circle diameter times B times ratio factor times the load stress all over the cosine of the helix angle squared. So the wear tooth load is to be calculated at 1,554, which is acceptable based on the references. Next slide, please. So lastly, we have the computed bearing sizes. So based on the table by Fairs, here are the parts, the bearing number and dimension for the sheave bearings and the gears. For the sheaves and the gears. So for the sheave, we have a bearing number of 309 as preferred, and the dimensions with bore of 45 millimeters, outside diameter of 100 millimeters, and a width of 25 millimeters. And for the gears, we have chosen a bearing number of 303 with the dimensions of bore at 17 millimeters, outside diameter of 47 millimeters, and width of 14 millimeters. Next slide, please. So thank you. That is all for our presentation. Thank you for listening.